Hello, so in this video we're going to kind of carry on with looking at special cases of second order ODEs. Okay, remember second order ODE is just the highest derivative that we've got in a differential equation, just the second derivative. That's why we call it second order. Okay, and basically, if we remember the last video, we kind of looked at the case where there was no y. Okay, so if we look at a general ODE, the variables, if you like, that we have. So we have the second derivative of the function, we have the first derivative of the function, we have the function itself, and we have some function that's just involving t. So those are kind of your variables that you should have in a differential equation. And in the last video, we looked at the case where there's no y, so there was kind of a y missing. Okay, and we found that we could just reduce it. We could reduce the order down to a first order differential equation. So we could go from a second to a first order and then just use a standard technique that we know and love, hopefully, with first order ODEs, and just go ahead and try and solve it now. Now what we're going to look at is we're going to look at an example where we're going to look at a slightly different example where we can again reduce it. So we can look at the other case when we can reduce the order. And we're going to look at using example again. And we're going to look at this case. We're going to have the second derivative plus y, so the function, times the first derivative cubed equals 0. Now notice first that this is non-linear. This is non-linear. Okay, so it doesn't actually look like this, which is a linear case. Okay, a linear case. So in other words, all of the derivatives are kind of separate. They're each in their separate terms, and also the highest, they're not raised to any powers or anything. Or the highest power, I suppose, is 1 that they're raised to. But here, what we've now got is we've got the second derivative of its own. That's that would be linear in that would be linear in itself. But now look, we've got the function multiplied by the first derivative. So already that's non-linear. But not only that, we've got the first derivative being raised to the power of 3. Okay, so instantly we know this is non-linear. Okay, but we can still work with this. So what have we got in this equation? So we've got the second derivative, we've got first derivative, and we've also got the function itself. Okay, but that's it. So in other words, there's no q of t. Q of t is the variable it's missing. If you look up there, q of t is the variable that's missing in this equation. Okay, and we can reduce this down. If this is the case, so in other words, our what we call our independent variable function, so in other words, our q of t, basically, our function which is involving t, if that's missing, so in other words, if this is all we've got, we've only got second derivative, first derivative, and the function, then we can reduce the order down. And it's exactly the same thing as we did before. We just let some new function, v, equal the first derivative. Okay, and you may be thinking, well, that seems a bit odd because I would probably introduce, v for y. We've still got the zeroth derivative, we've still got the function y. So why not introduce v for y? Well, if we introduce v for y, what do we end up with? We end up with v double dash plus v times v dash squared, cubed, equals 0. So it's exactly the same thing. We just replaced y for v. So it's not actually getting us anywhere. But look what happens if we introduce v for y dash. Well, if we introduce v for y dash, this is really saying dy by dt. Okay, this is really saying y dash is just the same as dy by dt, right? So now if we want to find y double dash, so in other words, the second derivative, okay, so in other words, the second derivative, so y double dash, well, if y dash is equal to v, okay, then y double dash must be equal to v dash. Well, we've said that v is equal to dy by dt. It's equal to dy by dt, right? So in other words, what we want to do is we want to find the second derivative of dy by dt. Well, we can use it by the chain rule. Okay, dv, v dash is the same thing as saying dv by dt, right? dv by dt, and then we can use the chain rule of this. The chain rule is just basically considering this as a fraction, okay, and we can introduce a new variable that way. And let's introduce our new variable y. Well, it's not really new, but we can introduce another variable. I shouldn't really say introduce a new variable, but let's introduce another variable. Let's introduce our y variable. So basically, we can rewrite this. We can rewrite this as dv, that's our dv part, okay, times by another fraction which has dt on the bottom, okay, and then in here and in here, as long as these two things are the same, they'll just cancel off. So in other words, we can introduce a new variable into, dv by dt. Okay, in this case, we're just going to introduce dy. Because look what happens if we introduce dy. By the way, they just cancel. So that's fine. That's all the chain rule is, by the way. We just, we can introduce a new variable. Yeah, it's sometimes called the outie-innie rule. But, in this form, it's fine. They're both the same thing. But anyway, we know what dy by dt is. It's this thing over here. So in other words, that's just v. So in other words, we can say that v dash is just going to be, we've still got dv by dy. We don't know what that is, unfortunately. Okay, so we don't know what v differentiated with respect to y is, but we do know what dy by dt is. It is v. Okay, it's this thing over here. Okay, so in other words, we can say now that y dash equals v, that's fine, but also y double dash is equal to v times dv by dy. Okay, so now we can just replace that into our function. So I'll just write my function out again. So let's replace it into our function. So y double dash is just going to be v times dv by dy. Okay, so that's taken that bit. We've just replaced, that by that. Plus y. Well, what was y? Well, we don't know what y is, so we'll just leave y alone. We haven't made a substitution for y. Okay. Times y dash cubed. So y dash was just v. So in other words, it's v cubed, and that's all equal to 0. Okay, so now look what we've got. Now look at what we've got. We've got, if we just consider that, there we go. What have we got in here? We've got v, okay, and we've also got the derivative of v, if you like. I mean, this isn't strictly speaking the derivative of v. It's the derivative of v with respect to y. But effectively, we can just treat this. This is still a first-order equation because we've got first-order differential equation because we've got the derivative and we've also just got v alone. And if you like, y is just our independent variable. So in other words, we can say that v is a function of y. So v is a function of y. Then we've got v and we've got v dash. That's v dash there. That's v dash there, and there's v and there's y. So in other words, what we end up with is a first-order equation. If you like, the y part is just replaced, our t in our usual equation. If we have, if we have in an ordinary kind of, in our second-order differential equation, our general form, we'll have a second derivative, we'll have a first derivative, we'll have a function, and we'll also have some function involving kind of our dependent variables. So say if we say y is a function of t, okay, y is a function of t, so it has t in, basically y is just a function that has t in, then we just have a function that kind of has just the t alone. It doesn't, it's not written as y as a function of t or anything. Well, this is all this y is doing now. So in other words, what we're saying is that y is just basically t. It's taken the place of t. It's not actually t, but we've taken the place of t. Okay, so hopefully you're kind of following that now. So if we like, that is what's known as our independent variable, because that is our variable that isn't written as anything. So y is, if you like, our free variable. It's our floating variable. It's not written as any kind of function. Like if we had y equals x squared plus 3x, for example, okay, we can write x as a function of x. But if we just write x on its own, okay, so it's just y. Okay, so we've, if you like, condensed x into this function of y. But if we just have x on its own, say x times y, then x, if you like, an independent variable, free variable, and that's all y is. That's all y in this case is doing. It's just playing the role of x. Okay. Anyway, this is a first-order differential equation. Well, look what happens if I take this yv cubed onto the other side. So we end up with v times dv by dy equals minus y times v cubed. That is separation of variables. That's separation of variables, right? Well, we can use separation of variables. In other words, if we get everything involving v on, say, this side, and everything involving y on this side, then look what we end up with. So we've already got a v here. So let's divide through by v cubed. Let's take this v over to the other side. Okay, so we end up with v over v cubed. We've still got dv by dy. Okay, equals minus y times, well, we haven't got the v cubed now. We've taken that over to the side. Yeah. And therefore, this then condenses down to 1 over v squared. This condenses down to 1 over v squared. Okay, and then if we take this dy over to the other side, look what we end up with, dy. That's just integration of variables. Stick an integration in front of both of them. That's integration of variables. We can work with both sides. Well, the integral of this side is going to be 1 over v squared integrated. So if we just write this as v to the minus 2 then, okay, and the integral is we just increase this power, so it becomes v to the minus 1, and we divide by this new power, so in other words 1 over minus 1, which is going to become a minus, right? And we can rewrite this v to the minus 1 as 1 over v, okay? There is an integration constant, but I'm going to write it kind of with when I integrate this one as well. I'm going to condense all the integration constants into one, okay? So the integration of this is fairly straightforward. It's going to be minus, raise the power by 1, so it's going to become y squared, and divide by the new power, so it's going to become half y squared, plus some constant integration. I'm going to call it c1, okay? So in other words, what I need to do now is I need to rearrange this to get v equals. So v equals, well, if I just multiply through by v, so let's have a look. Minus 1 over v is equal to minus a half y squared plus c1. If I multiply, well, first of all, let's get rid of this minus and this minus here. So let's multiply through by minus 1. Okay, this then becomes a minus. Okay, and then what I'm going to do is I'm going to multiply through by v. I'm going to multiply through by v. So if we multiply through by v, okay, this is what we end up with. Okay, and then I want just v on its own, so let's divide by all of this. Let's divide by all of this. So we end up with v equals 1 over half y squared minus c1. Half y squared minus c1. That's what v equals. But remember, we don't want what v equals. We want what y dash equals. Or we want what y equals. Well, we know that v is equal to y dash. We've set v equal to y dash. So in other words, if v is equal to this thing, then y dash must also be equal to this thing. So 1 over half y squared minus c1. That's just another differential equation. If I just rewrite dy by dt, that's what y dash is equal to. That's what y dash is equal to. That's equal to that. So that's another differential equation. Again, same thing as before. Let's just get everything involving y on the same side. So let's just move it over here. So let's just multiply by this denominator. So in other words, we end up with dy by dt equals 1 over, let's just write it out again, half y squared minus c1. Let's multiply through by this. Let's take, So let's take all of this. Let's take all of this over to the other side. Let's multiply through by that. Okay, I'm trying to be clever here. There we go. So multiply through by that. Okay, and we've still got 1 on that side. And let's just multiply through by this dt. Let's multiply through this dt. Okay, and then let's integrate both sides. Let's integrate both sides, and there we go. So we've just got an integration there. So this thing here integrated, raise the power by 1. So we got, so let's just raise the power by 1. So raise the power by 1, it becomes 3. And let's divide by this new power. Let's divide by this new power. So if we divide by this new power, this is going to become 2 times 3, which is going to become 6. Okay, so we've got rid of the integration of that one. Let's consider the integration of this one now. This one's straightforward. The integration of constant with respect to y is just going to be that constant times y. Okay, this is again fairly straightforward. It's just going to become t. Okay, and let's include our constant of integration now. So this is basically what we end up with. This is basically what we end up with. Let's just try and get y equals, or get everything involving y on one side. Actually, no, we can't do anything with that because it's going to have to write it implicitly. So, I mean, you can either leave it like that, or you can take the t and the c2 over the other side and just make it equal to 0. It's entirely up to you, but basically, as long as you put something that looks like that down, then that is your answer. So let's just do a brief summary of the last videos, the last 2 videos of reduction of order. So basically, a second order ODE will have the variables the second derivative, the first derivative, the function itself, and also some function involving y, and so involving t. Sorry, so just our independent function. So that's what our second order ODE should have. It should have those 4 things in. Okay. If these last 2 things are missing, though, we can do something with it. We can do something with it. If this first thing was missing, by the way, it's just becoming, if that first thing is missing, then therefore that just becomes a first order ODE because the highest power is 1, so that's fine. Okay. If this first derivative is missing, however, we can't really do much with it. Okay, and we have to actually solve it in the way that we have to solve it if all of the variables which are missing, all the variables are there, which is what we're going to do in the next video. Okay, so basically it's only the case when these last 2 things are missing, so that either the function involving y or the function involving the independent variable is missing. Then we can do what's known as a reduction of order. Okay, so first case we considered was no y. Okay, so if there's no y, so in other words, if that was missing, then basically what we had was the second derivative, the first derivative, and the function involving t. Okay, and then all we did is we just made a substitution, so we let v equal y dash. Okay, and then therefore we can just say that maybe if I write it around the other way, so y dash equals v. Okay, then therefore the second derivative is equal to v dash, and we just make that substitution in there. And then basically we just solve that usually by integrating factor. Okay, usually by an integrating factor. Then if we had the case when there was no function of independent variables, if now that case was missing, okay, then basically what we were left with, we left the second derivative, first derivative, and just some function involving y. And it's usually the case when it's linear. Okay, it's usually the case when it's linear. Non-linear. Then basically all we did is we just let y dash equal v. Okay, and then this time y double dash, we had to use the chain rule to find out that y double dash was v dv by dy. And if we make those 2 substitutions, then usually we can just use separation of variables. So this one was using integrating factor, integrating factor, and this one was using separation of variables. Separation of variables. Okay, so basically, those are the two cases. So in both cases, just let that equal to, let v equal to the y dash, v equal to the first derivative in both cases. Okay, you can see that there. And then just with no y, you have to be a little bit, you can do it's fairly straightforward. You can just let y dash equal v dash. But with the second derivative, with this case where there's no function of independent variables, you have to be a little bit more careful, and you had to basically use the chain rule to derive that. Okay, but I mean, in both cases, as long as you let that equal to that, it should be fairly clear what to do from there.